Welcome to Basic Mechanics, a critical look. This is lecture number 5. Now, in the past lectures, we have been taking a critical look at the 3 basic laws of Newton. In particular, we have spent a lot of time talking about the first law. We will come back to the second and the third laws and some details about them later on, but for the time being, let me point out one very important issue. The 3 laws of Newton, as originally written down, are actually applicable to point particles. However, even from the very first lecture of this series, and I'm pretty sure this is no exception to any other course of mechanics anywhere else, we start out by talking about bodies which are perhaps quite large. For example, in the very first lecture, we talked about a book sitting on a table and tried to use Newton's laws for that. If the laws are actually meant for point particles, what sense does it make to use them for large bodies? This is the question that we are going to address today. And in order to address that, we need to talk about what is called a system of particles. Now, let us focus on this particular picture here, where I have tried to draw green dots. These should have been 0-dimension dots for point particles, but since 0-dimension dots would not be visible, I have drawn green circles here. These are point particles which make up my system. Now, in order to emphasize the fact that the system does not have to be everything under the sun, I have also drawn the positions of a few other points in purple here. These are points which are outside my system. So you could have point particles which are part of your system. You could have other point particles outside your system. And when you're talking about a large extended body, you can think of that as being built out of very many number of point particles. Now, exactly which one of the particles should I consider to be part of my system? That is entirely up to me. Depending on convenience or depending on the question that I want to answer, it may be a good idea to change exactly what constitutes a system from case to case. Even when you're solving one problem, you may want to solve a part treating, say, 10 particles in your system as a whole as the system. For another part, you may want to consider only 5 of them as your system and treat the other 5 as external particles. Now, what we have shown here is the coordinate frame of reference, the x, y and z axis for an observer O. We are assuming that the observer O is inertial. So Newton's laws can be applied for point particles in this frame. And in this frame, what we have are all these particles in my system of masses m1, m2, m3 and so on are labeled here, and what we are doing is we are considering position vectors drawn from the origin of my coordinate system to each one of these particles and calling them R1, R2, R3, etc. So if there are n particles, the final one would be labeled Mn for mass, and we'll have a position vector according to our observer given by Rn. Let us focus on a particular one of this set, the ith one, and its mass is Mi and position vector is Ri. Now this is a point particle. Our entire system may be a collection of lots of particles, but each individual particle here is a point particle. And so I can definitely use Newton's laws for it directly. And remember, we have assumed that our observer is inertial so that we can use Newton's second law here. So, mass of the ith particle times the acceleration of the ith particle, mi times d2 ri dt2 is equal to Fi, the force acting on the ith particle. This is the total force acting on the ith particle, which can be broken up into 2 pieces, Fi external and Fi internal. Now Fi external, this force, is the force acting on the ith particle whose cause is any particle or particles outside my system. So if any one of these purple colored particles here exert a force on Mi, this particular ith particle, that force is going to contribute towards Fi external. Of course, when I say Fi external, I will add up the contribution to the force on the ith particle given by each and every body which is outside my system. Now what about Fi internal? This is the force on the ith particle given by all the other particles in the system. So, if you label the force acting on the ith particle due to the jth particle of the system by Fij, what you have to do is sum it up over all possible values of j running all the way from 1 up to n, with one exception. You have to leave j equal to I out of this sum. Of course, a particular particle will not exert a force on itself. That is why you need this I not equal to j condition here. You could of course have dropped this condition and simply said Fii is by definition 0. In which case, of course, dropping this condition would have made no difference. Now, with this in place, we can rewrite our second law for the ith particle in this particular manner. Mi d2 ri dt2 is equal to the force on the ith particle, which is Fi external plus Fi internal, which is the sum over j going from 1 to n, Fij. Again, remember, j is not equal to I in this sum. Now this is the equation for the ith particle. What we want is an equation for the whole system. How do I get an equation for the whole system out of this? Simple. I just add up all the equations that we have for each and every one of these particles. You have an equation like m1 d2 r1 dt2 is f1 external plus f1j summed over all j running from 2 to n. We have another equation m2 d2 r2 dt2 equals f2 external plus f2j summed over all j from 1 to n, leaving out 2, and so on. We will just add all of these equations together, and that is what we write down here. I am just summing up the ith equation from I equal to 1 to I equal to n. We are of course summing up both sides of the equation. On the left hand side, we have this quantity mi d2 ri dt2 summed up from I equal to 1 to n. We will have a lot more to say about this quantity in the rest of this lecture. For the time being, let's focus on the right hand side. The right hand side is I equal to 1 to n sum of Fi that can be broken down into two pieces. Fi external can be summed up, has to be summed up from I equal to 1 to I equal to n, and this sum over j has to be further summed up over I. So we have a double sum, a sum over both I and j. And once again, the j is not equal to I stipulation holds here. So in this sum, you have all terms possible for all values of I and j running from 1 to n, barring terms like f11, f22 and so on. Now, this is the most complicated piece in this whole equation. So let us take a look at this in some more detail. Firstly, how many terms are there in this double sum? Note that I can take any one of the n possible values from 1 to n, but once I have chosen I, j can only take n minus 1 values, all the n values barring I. Which means for each of the n values of I, there are n minus 1 possible values of j. And that this gives rise to n into n minus 1 terms here. Just to point out, even for such a modest value of n as 10, For a 10 particle system, n into n minus 1 becomes equal to 10 times 9. That's 90. So there will be 90 terms in this sum if you are dealing with only 10 particles in your system. If you are dealing with 100, of course, this becomes 9,900 in number. And you can easily imagine how big it is going to be for a macroscopic object when you think of each of its atoms or molecules to be their point particle constituents. That's a mind-bogglingly huge number to worry about. And if you really had to worry about the sum, you would hardly be able to do anything when dealing with an extended object or a system of particles. Luckily for us, this immensely complicated looking term simplifies a lot. What saves the day for us is the fact that this sum has pairs of terms which cancel among each other. Note that I and j take all values ranging from 1 to n. That means f1 to I equals 1, j equals 2 will be a part of this sum. But then again, so will f21, I equals 2, j equals 1. In general, I equals p, j equals q. This term will be there as long as p and q are different. But then fqp, I equal to q, j equal to p term will also be there. So we can break up this double sum into many pairs. fpq plus fqp will be there, and then of course you keep on changing p and q, and you get more and more terms in the whole sum. But notice, in this pair, fpq is the force acting on the pth particle exerted by the qth particle of our system, whereas fqp is the force acting on the qth particle exerted by the pth particle of our system. But this is exactly what we mean by action-reaction forces. If body A exerts a force on body B, then body B exerts an equal and opposite force on body A. So if you call FPQ the action, FQP will be the reaction. Of course, let me stress once again, as I have done before, which one you call the action, which one you call the reaction is entirely up to you. Be that as it may, FPQ plus FQP will always vanish because the two forces, being action-reaction forces, have to be equal and opposite to each other, and their vector sum is 0. And therefore, Newton's third law ensures that each pair in this sum vanishes, and since the sum is made out of pairs just like these, and only pairs such as these, the sum, this big double sum, will vanish at the end. So, in this summed up equation which we wrote down for the whole system, you just have this and this term vanishes. So finally what you end up with is sum over all I running from 1 to n, mi d2 ri dt2 is the sum over all I running from 1 to n again of fi external. The internal forces all cancel among each other. And this sum, the sum over all I of Fi external, is what we call the net external force on the system, F external. This equation, or rather a slight variant, is called Newton's second law for a system of particles. However, let me emphasize that in its derivation, we used not only Newton's second law, Newton's third law, of course, played a huge role. And not only that, the very fact that we could use Newton's second law in the very first place means that Newton's first law must have held for the observer that is being used. So, frankly, all three laws of Newton actually went into proving this particular equation. Now, as I said, what is actually called Newton's second law for a system of particles is a slight variant of this. And that essentially depends on rewriting the left-hand side of this expression in a slightly different manner. But before we go there, let me answer the one question that we started this particular lecture with, which is how do we often use Newton's second law directly for an extended body as if it was just a point particle. You just use mass times acceleration equals F. Now, what you have here, of course, is the sum of mass of the ith particle and the acceleration ai of the ith particle sitting here. So this is sum of mi ai. That's what we are really summing up on the left hand side. Now when we have a system of particles, different particles in the system may be moving with different acceleration. That, of course, is the most generic situation possible. However, there is one case where we have a much simpler scenario. And this is the case of a rigid body which is undergoing a special kind of motion called translation. So for rigid bodies, undergoing translation, something very special happens. But to understand that, we have to first understand what exactly a rigid body is. A rigid body in physics is an idealization. No real object is a perfectly rigid body, but we have many bodies around us which are very good approximations to that. And when we do usual calculations, we treat them as rigid bodies. The idea of a rigid body is the following. It's a body such that if you think of it as made out of different particles, the distances between all these particles, all these distances are held fixed. They don't change with time. Now, if you consider any 3 points on a rigid body, let's say this one, and this one, and follow them as the body moves, the pairwise distances between these 3 points stays fixed. They are the same in the new position of the body as in the old position. Of course, that means that the triangle formed by the new positions of the 3 points is congruent to the triangle that has been formed now. An immediate consequence of that is not only do the distances do not change during a motion of a rigid body, neither do angles. So that simplifies the motion of a rigid body a lot. By the way, when I say a lot, I mean compared to a non-rigid body. The dynamics of a rigid body is in itself a very rich and complex subject. So when I'm saying that it simplifies a lot, it's in comparison with what would have happened if this assumption of rigidity was not made. Now, the major kinds of motion a rigid body can have are being shown in the pictures here. This one is an example of a motion where this light blue object is the initial configuration of the body and the green one shows its position after a while. Now here you can see that each part of the body is essentially parallel to its original position. So if a motion happens like this, then you say that the rigid body is undergoing translation. Another common motion which a rigid body can have is one in which a point, if we are talking of a two-dimensional rigid body, or a line, if we are talking of a three-dimensional body, of the body stays fixed, at least instantaneously fixed, and the body turns around that. Such a motion that has been depicted here is called, obviously, rotation. Now, it turns out that there is a pretty standard theorem that we can prove, and we will talk about this later as well, that the most general motion that a rigid body can have is a combination of the two. You can have a translation followed by a rotation, or vice versa. For example, in this picture what we see is that we could have translated this object to the position like this, where of course it would essentially end up looking like this. And then you could rotate that thing around to get to the final configuration. So the most general kind of motion essentially is this, a combination of a translation and a rotation. But let us now focus on the simplest possible kind of motion a rigid body can undergo, which is a translation. Now, let us focus at a particular point on the rigid body at time t0, that is, in the original configuration. At time t, in the displaced configuration, the rigid body will behave in the following manner. If you follow the displacement of this particular point from here to here, you of course will get a particular vector. The point is, under translation, each and every point of the rigid body gets displaced by exactly the same amount. We have shown that in this picture here. This point gets displaced here, this point gets displaced to this point here, this point gets displaced here, and so on. And the displacement vector of each one of them is one and the same, namely delta. So, in terms of the position vectors measured by our observer O, if say the ith body was here at time t0, Ri of t0 were the position vector of that, and at time t it's landing up here at Rit, then Rit minus Rit0, this vector, the displacement of the ith point, can be written down as delta vector, which is the same regardless of which value of I you use. Same displacement for all particles. This is a feature of rigid bodies undergoing translation. Now, of course, if this is true, then the derivative of this expression immediately tells us that dri vector dt, which is of course d delta dt, is the same for all I. So each point particle making up a rigid body has exactly the same velocity when the body translates. And obviously one more differentiation will tell you that the second derivative d2 ri dt2 is also equal to the same value a for each and every I. So what we have is a situation where the sum on the left hand side of our version of Newton's second law, that is sigma I going from 1 to n, mi d2 ri dt2, can be simplified considerably. All the terms here, each and every one of these factors d2 ri dt2 are the same, namely a, which we can now call the acceleration of the body itself. And now, in this sum, you can easily take a, which is independent of the I, out of the sum. And so you are now left with sum of all mi's, which is of course nothing but the total mass capital M of the rigid body, times a, the common acceleration of every point of the rigid body. And this common acceleration, as we have already said, is what we call the acceleration of the rigid body. So now, for a rigid body undergoing translation, we can actually use Newton's second law in just the original form which is valid for point particles. Sigma mi d2 ri dt2, the left hand side of our Newton's second law for a system of particles, simply becomes capital M times a, and that is equal, as we have already seen, to the net external force F external. The only difference between the point particle version of Newton's second law, the actual second law, and this one is here the force exerted is a net external force. Of course, if when we were dealing with a point particle, all forces had to be external, so you did not bother saying external there. You just had mass into acceleration equal to the force acting on the point particle. Here, for a rigid body, once again let me emphasize, under translation, total mass of the rigid body times the acceleration of the rigid body is equal to the net external force. Now this explains why in many problems that we have done, we could treat extended objects as if Newton's second law directly worked for them. We were essentially talking about translating rigid bodies, for which this equation works as it is. Now let me warn you that for a general motion of the rigid body, a motion like this, different points get displaced by entirely different amounts. So even for a rigid body, different points are displaced differently They have different velocities, different accelerations. So you cannot use mass into acceleration equal to force, even if you were to use only external force, for a general motion of a rigid body. Of course, you cannot use this at all when the system under consideration is not even rigid. You don't have a common acceleration of the body, so you cannot use mass into acceleration equal to force. What to do in such a case is what we will consider next. Now it turns out that even in such cases, such much more general cases, we can still use an equation which is very much like this. But that equation has to be written down for a very special point in the system. To see how this comes about, let us fall back on our Newton's second law for a system of particles once again and try to rewrite this left-hand side in a rather special manner. Now this rewriting involves very simple properties of differentiation. In this product here, mi, the mass of the ith particle, is of course the same at all times. So it's a constant as far as the time derivative is concerned, which means I can pull this inside the time derivative. I can form mi ri vector first and then differentiate that twice with respect to time and then add up over all possible values of I. And of course that this will be exactly the same as what we started out with. The next property that we use of derivatives is just as simple. The derivative of a sum is the same as the sum of a derivative. Here you have sum of a lot of double derivatives. They're the same as a double derivative of the sum of these quantities. So sigma mi ri summed over from I equal to 1 to n is being differentiated twice on the left hand side of our equation. Now, let us focus a bit on this. Sigma mi ri. This cannot be a displacement vector or a position vector for a point particle for the simple reason that it has the wrong dimensions. Each term in this sum is a mass times a length. So it has an overall dimension of m times l. A position vector has to have dimensions of length. But that is easily remedied. You can convert this entity, which has dimensions of m times l, into something of dimension l by dividing by some mass. Now the only mass that you can really think about naturally here is the total mass of all the particles in the system. So if you divide this sigma mi ri, sum of all the mr contributions, by the sum of all the masses, you do get a vector. Of course, this is a vector divided by a scalar, so this has to be a vector, which has the correct dimensions to be the position vector of a point. Now this position vector we call R vector, capital R, and when we want to be extremely careful in pointing out what we are talking about, we will call this RCM. CM stands for center of mass. So what we have done here is we have used this construction to define a special point corresponding to the system. This is a kind of weighted average of the position vectors of all the particles which make up my system. And as we have just said, it has a special name simply because it's an important concept. Why? You will soon see that. Now, once you have done this thing, this left-hand side of our Newton's second law for a system of particles simply becomes second derivative of the product of capital M, which is of course the sum of all the masses here, times R vector. And that means it's equal to capital M, once again capital M being a constant as far as time is concerned, can be pulled out of the derivatives, capital M times d2R vector dg2. So, for a system of particles, we have this very interesting looking equation. Capital M d2R vector dg2 is F external. Now what does this really imply? The first thing that you should notice is that this looks exactly like Newton's second law for a point particle. where you have the mass of the point particle times the acceleration of the point particle equals the net force acting on it. Here what you have is total mass of the system times acceleration of this special point, the so-called center of mass, is equal to the net external force. Now we can interpret this physically in the following manner. When you consider the motion of a system of particles, its center of mass in particular moves in such a way as if it were a point particle where all the mass of the system were concentrated and on which the entire external force acting on the system were to act. So, although the overall motion of a system of particles may be very, very complicated, with different parts of the system moving with different velocities, different accelerations and whatnot, the center of mass executes a particularly simple motion. Let me illustrate that with an example. Consider a club which a juggler has thrown into the air. Now the club is a rather irregularly shaped body and it tends to tumble and move in a very complicated manner through the air in its flight. However, no matter how complicated the motion really is, if you look at one specific point, the center of mass of the club, and follow it as it moves along, it actually executes a very simple path. If you ignore the presence of air resistance, then that path would be none other than the parabola that we all have learned about when a point particle is thrown at an angle to the vertical. The center of mass will behave exactly like that point particle. It will behave as if the entire mass of the club is concentrated at one point and the net external force, which is the total mass of the club into the acceleration due to gravity, would also behave as if it were acting there. Of course, this is only as far as the motion of the center of mass is concerned. If you look at the other parts of the club, they will execute a much more complicated motion. Simply because it's not only gravity which is acting on that, but also the forces due to the rest of the club. So internal forces also become important when you want to analyze the motion of some part of the overall system. But if you only look at the center of mass, you don't have to worry about the internal forces at all. Now we will have a lot more to say about the center of mass and its implications as far as the physics of a system of particles is concerned in the next lecture. But before I sign off today, I want to show you another way of rewriting the left-hand side of our Newton's second law for a system of particles. And this other way will also give you a very important insight. This other way involves starting from the left-hand side of our version of Newton's second law for a system of particles and focusing on an individual term in the sum. The individual term, of course, is the mass times the acceleration of the ith particle. Now, it's easy to see that we can rewrite this as the derivative of mi dri dt. Since mi is a constant, it does not change with time, it can be easily pushed inside one of the derivatives. Now, the reason why this is a useful form is that the quantity in the brackets in here is simply what is called the momentum of the ith particle, pi. And in fact, this should not come as a surprise because the original version of Newton's second law, even for a point particle, stated that the rate of change of momentum of a particle is equal to the net force acting on it. And there what we did was use the fact that the mass of the particle is constant to rewrite that in the form of mass times acceleration is equal to the force. Now, once we plug this in, the sum on the left hand side simply becomes a sum from I equals 1 to n of dpi dt. And once again, because the sum of derivatives is equal to the derivative of the sum, we can rewrite this as ddt of the sum of all the momenta of the individual particles, and this can be written as ddt of capital P, where capital P is simply our notation for the net momentum of the system of particles, something we get by adding up all the individual momentum vectors. So Newton's second law in this version becomes simply dp dt equals F external, the rate at which the net momentum of a system of particles changes is equal to the net external force acting on it. So at this stage we have two versions of Newton's second law for a system of particles. Mass of the entire system into the acceleration of the center of mass is equal to the net external force acting on the system, and this one, rate at which the net momentum of the system changes is equal to the net external force acting on it. Perhaps it is this version which is more often called Newton's second law for a system of particles. And the reason why this is perhaps better known is because of a corollary which follows immediately from this statement. If there is no net external force acting on a system, then the net momentum of the system is conserved. It maintains whatever value it has at the beginning of the motion. This statement, the law of conservation of momentum, is a central feature in all of mechanics, and therefore we will definitely have a lot more to say about it in a future lecture. We will meet again soon. As promised, we will first talk about the center of mass and its physical significance in a lot more detail. Bye till then.